Hey physics students, welcome back to the lecture videos. We're going to try this again with a little bit of a twist on it. We're going to make these videos as short as possible and do a little bit more example problems in class. So hopefully you like it a little bit more. All right, so Unit 3 is another approach in how we solve motion problems in terms of energy and work. And you've already done an introduction lab by this point about the different types of energy. So we'll talk a little bit more about them, but we'll also talk about work, which is where energy comes from. So we're going to start off real easy, and we're going to take a look at the basic energy model. I'm going to do this in class, but when you think about, many of you have part-time jobs. So when you think about your paycheck, you get some money that comes in. That's your paycheck, right? But then you have all these things that are in the red, right? You got to pay for your car. You got to pay for your insurance. You got to take your girlfriend out to the movies. You got to eat. You got to take her out to dinner after the movies, right? You got all this. Oops. You got all these things that your paycheck ends up going to. That go, and the question is, did you lose money? Well, no. But that money is now represented in terms of different things. And if you pay enough money, then you'll have a happy girlfriend. But you have these other things that represent what your money initially was. So that's the same concept with energy, is that energy can become different things. So in the basic energy model, every system, we have some total amount of energy. We use a capital E for that. Like your paycheck, the energy can be turned into other types of energy, but they're still always a part of this whole E that we started with. Energy is never created or destroyed, only transformed or transferred. Transformed means it's changed into something else. Transferred means it's removed from the system, and we'll talk about that as we talk about work later on. Okay, so this might still seem a little confusing, so we got to talk about some basic types or forms of energy. The first one is one of the most common that we will be looking at, and that's kinetic energy. And kinetic energy uses the symbol K, and it's the energy of motion. It's the energy associated with having a velocity. Gravitational potential energy, well, when I think about that, the root word is gravity, and then the root word is potential. So that's just if I'm some height above the ground, in this case I have this whole hill to go down, I have stored energy that's just simply associated with that height. Okay, we use this symbol UG, U meaning potential and G meaning gravitational. Elastic or spring potential, we've talked about springs before, and springs always want to be at equilibrium. So that's energy stored when a spring is stretched or compressed from that equilibrium point. And for that, again, it's potential, so we use U and S for spring. A couple other forms that we'll talk a little bit about, but not as much. The first one is thermal, and that's essentially heat, which is molecules moving. So when we think about thermal energy, that's typically caused by friction. And if you're rubbing your hands back and forth, for example, that's causing heat. But really, that's coming from kinetic energy, the energy of motion. We just use E subscript TH for thermal energy. Chemical energy, this isn't one that we'll talk about unless you take AP Physics 2. That is E subscript chemical, and that's energy stored in the bonds between molecules. So like when you eat something, your body digests it. Don't ever eat the whole stem of an apple. It's disgusting. Okay, and then finally another AP2 topic we have is nuclear energy, E subscript nuclear, and that's energy stored in the mass of the nucleus of an atom. And that's a very, very complex topic that we spend some time talking about in Physics 2, but that's where nuclear, when you think about nuclear reactors and stuff like that, that's what they do, is they use that energy that's stored in there to help generate electrical power. All right, so energy transformation. So going back to this concept of your paycheck, we can transform one type of energy to another type of energy. So here in this picture we have potential energy, but then as he pushes the ball down the hill, that potential energy turns into kinetic energy. And again, you should have seen that in your lab. So there's this little flow chart: kinetic going to potential, potential going back to kinetic, potential going to chemical, chemical going to kinetic, going back. There's all these back and forths. And then there's these orange lines, and all of these orange lines all lead to one place: thermal. And notice how thermal doesn't go anywhere else. Once energy becomes thermal energy, it's essentially lost or useless to us. There is no way of getting that back. So think about when your car comes to rest, right? Your brake pads heat up. There's no way in getting that energy back. Now, when you talk about things like the Prius, there are some other technologies that are utilized, but once those brake pads are heated up, there is no way to get that energy back. It's lost. Okay, so thinking about energy transformations, here we have a weightlifter creating gravitational potential energy from the weights and from the chemical energy that's stored in their body. This person in the swimming pool, they push down the springboard so it becomes elastic. That launches them up and that becomes kinetic. At this top, there's gravitational potential, and then as they come back down, they're back into kinetic. There are so many things that go back and forth, but when you're comfortable with the different types of energy, it's really easy to keep track of. We didn't actually do the roller coaster simulation, but we did simulations that were similar with our lab. But one of the things you should have noticed in your lab is that the total energy should always have stayed the same. And we see that in this graph right here, right? This red represents potential energy. This green represents kinetic energy. The orange represents dissipated, aka thermal energy. So therefore, the energy is not created or destroyed. It's only transferred or transformed. So we got a quick check. A child's on a playground swing, motionless at the highest point. What energy transformation takes place as he goes back down? Well, at the highest point, they have potential energy. And as they swing back down, that becomes kinetic energy. Another one, a skier is gliding down a gentle slope at constant speed. Well, they have all this potential energy as they're going down, but they're not increasing their kinetic energy. Therefore, that potential energy is actually going straight into friction. All right, so the next question is then, we got these quick little types of energy. Where does energy come from, or how do we describe why we have energy? And we do that we explain it by describing this concept of work. Work is the mechanical transfer of energy into or out of a system by pushing or pulling it, essentially exerting a force. So energy can be transferred into a system by doing work. And if you think about like your job analogy, you do work to get money. You earn an hourly wage for a number of hours you worked to get money. You exert a force over a distance to do work to get energy. We also have this concept that you saw in the lab about heat. Heat's the non-mechanical transfer of energy between a system and the environment, aka thermal energy or friction. But we do dive a little bit more into that in AP2. So on our diagram on the right over here, you see that work is either putting energy into a system, or heat or thermal energy is taking energy out of a system. So when I think about this little example over here, the person on the bike, they're doing work to put energy into the system. Well, what type of energy are they getting? They're getting potential energy. They have potential energy at the top of the hill. Then, as they go over the hill, they can just get kinetic energy because the hill, or gravity, you could say, is doing work to pull them down the hill. So that's how that energy goes. Okay, so this athlete over here, there's a shot put here. They do work, giving it kinetic energy. You exert a force on a match to do work that creates this thermal energy on the match, which causes it to light. Your body does work. You're pulling a slingshot back, giving it elastic potential energy. When you release it in a slingshot, it has kinetic energy. So all these things, you're doing work. You're exerting a force over a distance. All right, so we got a quick check. A tow rope pulls the skier up a hill at a constant speed. Energy transfer is taking place. Well, the toll rope is doing work to bring you up the hill, so it's giving you it's giving you potential energy. There's probably some speed associated with that, so you're also getting some type of thermal energy. I'm sorry, some speed, so you're also getting kinetic energy as you go up the hill. So as we continue to go through this unit, we're going to take a look at the work energy equation, and we're also going to take a look at the conservation of energy. And the work energy equation's a pretty simple thing. It's just saying that whatever work that you do is equal to how much energy you add into the system. If there's no energy being transferred into our system, then it's called an isolated system. And we'll take a look at that later. And that means that whatever energy I start with, I'll have to finish with. And that's going to get us into the law of conservation of energy. And from this, we'll be able to start analyzing and solving problems. All right, got another quick check. This one's kind of weird. A crane lowers a girder into place at a constant speed. Consider the work done by gravity and the work done by tension, which is true. Well, gravity is actually decreasing as it goes down. So therefore, that force is going downward, and that work done by gravity is positive. So it's either A or B, but the tension, the upward tension, is the direction opposite of the motion, so that's actually negative work. So right there, so our correct answer is B. And that might seem a little confusing, and it is, but we'll talk more about work in the next section. Okay, so one last just thing to bring it all together. What we're getting into in this unit is the law of conservation of energy. The energy of an isolated system remains constant. We can transform energy from one type to another type, back and forth, whatever, until we make thermal energy. And where does that energy come from? Well, we do work on the system to put in energy, so that changes the amount of energy. So we'll talk and we'll use this throughout this unit as a basis for how we can solve problems. But energy is just another way of explaining and quantifying a physical characteristic of an object in its environment. And that was a quick little introduction, and next section we'll talk more in depth about work.